Gay-Lussac. Okay? So you remember he did work with gases that we talked about in the last chapter. He also looked at gas volume and reactions. So when you have a reaction going on that involves multiple gases as reactants and or products, things get a little bit tricky. It's hard to take the mass of a gas, we know this. The mass of a gas is challenging. But volume is pretty easy. That's the easiest thing to measure about a gas. So Gay-Lussac looked at gas volumes, and specifically he looked at the combustion of hydrogen. This is what goes on in a hydrogen fuel cell vehicle. You take hydrogen, you combine it with oxygen, the only byproduct is water. Very nice. Very nice to have a combustion reaction that only produces water. Well, if you take 2 liters of hydrogen and 1 liter of oxygen, you get 2 liters of water. Does that seem odd? Does it feel like you should get 3 liters of something?
Yeah.
Yeah. And this is before, remember, this is before we knew anything about diatomic molecules. It was not known that there were some things that had 2 atoms stuck together. So Gay-Lussac is looking at this and he's saying, okay, so I've got a 2 to 1 to 2 ratio. Well, that's small whole numbers. And if you think back to law of definite proportions, law of multiple proportions, we have that small whole numbers thing a lot. So what this leads to is the law of combining volumes. And all it says, it's very much like the definite proportions and multiple proportions. It's just saying, if we don't change the temperature and pressure, we have to specify this because we're now talking about gases, the volumes of those reactants and products are going to be small whole number ratios. So, which is sounds more complicated than it really is. It's not that hard. So then we come back to Avogadro, our dear friend, old Emilio. The problem is, if we don't know about diatomic molecules, and we take 1 unit of oxygen and 2 units of hydrogen, and we make 2 units of water, it seems like we must have split that oxygen unit. Well, if the unit for oxygen is a single atom, then what did we just do? Split an atom. Which, per Dalton and atomic theory, we can't do. And we know we can't do it and still have the same substance. So this is a problem, and this is what starts to make Avogadro think, maybe some things are actually made up of 2 atoms together. And most of his work actually comes down to counting things. So he gets this idea that we have diatomics, but what he states and what's important is he says, if I have an equal volume of 2 gases, if I have 1 liter of gas A and 1 liter of gas B, their temperature and pressure are the same. Guess what else is the same? The number of pieces, the number of particles, the number of molecules. And this is Avogadro's law. Remember, Avogadro's all about counting things. He counts. This gives us this idea that as long as temperature and pressure are the same, the only thing that's going to change the volume of a gas is the number of particles. And now we say the number of moles, because we have that idea. He was also the first to propose that we had diatomic molecules. How many diatomic molecules are there? Do not shout it out. Hold up fingers. Wait, easy rhyme to remember it. Uh-huh. No. Heavenly 7. 7.
Oh, no.
Yeah. So it's the halogens, iodine, bromine, chlorine, fluorine, and then hydrogen, oxygen, nitrogen. So heavenly 7. They're always gases. And Avogadro was the first to propose that. Okay, so this solves our problem of splitting up oxygen. If we have a volume of oxygen and it's really made up of O2s, then we can break it in 2. We're not violating that idea that the atom is indivisible. So actually, the combustion of hydrogen is the thing that confirms that. All right, now the other thing that Avogadro gives us is this discussion of gas volume and the fact that it's proportional to the number of molecules. So what we're saying is that temperature and pressure don't change. Notice that they're not in there. Because when something is not changing, we don't put it in the equation if we can help it,
Right.
because it's not changing. So volume is equal to some constant number times the number of moles of something.
Was this in our test?
No, but it's similar to ideas. The part that we did not talk about in the last chapter was moles. So we talked about volume, temperature, pressure, but we never talked about moles, because that's really this chapter, the stoichiometry piece. Okay, so here's what Avogadro's stuff leads us to. At STP, 1 mole of gas occupies 22.4 liters. I want you all to emblazon in your brains number 22.4. 22.4 liters, not ducks, not dirty socks, not M&Ms. 22.4 liters. At STP, that's the other big piece. So, when you are 22.4 years old, you'll probably be what, in your last year of college? You'll be 22 in about 5 months.
You mean 23? Oh, 22
in about 5 months,
I think
yeah.
in 5
Oh,
months.
no. And about, yeah, around about there. So, 22.4 liters at STP. Doesn't matter what the gas is. Doesn't matter if it's hydrogen. Doesn't matter if it's helium. Doesn't matter if it's carbon dioxide. Doesn't matter if it's chlorine gas. Doesn't matter what the gas is. 22.4 liters. 22.4 liters. Only at STP. So, I'm going to do a little quick quiz here.